Hey there! Here we go into lesson 4, the integral and p-series tests. In this first video in this lesson, we're going to talk about the integral test for convergence and divergence of infinite series. This test is tested on the BC exam, and it is one of those tests where it comes up a decent amount even in college classes too. I'm on this test. What I mean by that is, it's cool, but it really sets the stage for the p-series test. More on that in a little bit. So for now, we got to figure out when do we use it and what does this integral test tell us? So the integral test basically starts out like this. Given that you have an infinite series, right, some a sub n, so n equals 0 to infinity, you're adding up some sequence a sub n. And the fact that you've got some function, f of n is a sub n. Like if a sub n was n, then f of n would be equal to n. You got to have that function, that a sub n value has to be positive, continuous, and decreasing. Why does it have to be those three things? Well, we're going to take a look at that in a little while. So for now, just know that we've got to have those three conditions met. If the integral from the improper integral from 0 to infinity, or 1 to infinity if that was 1, or 2 to infinity, it's got to match that bottom index, of f of x dx converges, then the sum also converges. So it's basically they match each other up. If the infinite integral from 0 to infinity of f of x dx diverges, then that very same series with the same function in it that is positive, continuous, and decreasing diverges. So basically, whatever the improper integral does that matches with your series, that's what your series also does. Again, the series must be positive, continuous, and decreasing. So when do we use it? So if your summand, a sub n, or the sequence, is easily integrable, you look at it and you're like, oh, I could integrate this thing, and it's positive, continuous, and decreasing, then you know that the integral test is a good one to use. I don't use this very often unless I'm looking at my summand, the thing that I'm expanding out there, and I'm like, all right, it's very integrable, and I have no other test that works. Or if I've got some kind of problem where an integral's involved, and it's very clear that the problem, or whoever gave me the test, wants me to use the integral test. That's about when I use it. So it says determine if each series converges or diverges. We're going to practice using the integral test here. So if we look at this series, let's expand it out. Expansion is our friend after all, right? So 1 over 1 plus, and this would be 1 over 2, n equals 2 goes next, plus 1 over 3, plus 1 over 4, plus, and it goes on until we get to 1 over n, and it keeps on going. What you should notice is that every single term in this series is positive. Yes, it is. All those numbers are positive. We certainly have a continuous function, right? The function 1 over n is continuous, starting at 1 and going on. That's true. And the values are decreasing in size as we go down. So we fit all of our check marks, right? So I'm going to actually state that out and formally say, since 1 over n is continuous, I'll abbreviate. Of course, you wouldn't do that on a test. You know what? I won't abbreviate. I won't be lazy. Since 1 over n is continuous, positive, and decreasing. That's important. And I'll say that over n is greater than or equal to 1, because that's where we're starting at. The integral test may be used. So the integral test can be used. And we still have yet more to do. So I'm just kind of setting the stage and saying, yo, we can use this integral test. I'm not saying yo, though. So we're now going to take a look at the integral that matches this sum. Start at that bottom value 1, go to infinity, of 1 over x dx. You could also do 1 over n dn. It wouldn't matter. This integral is equal to ln of the absolute value of x, very simple integral, evaluated from 1 to infinity. So here's the one thing. I guess what I should have done here, to be very, very formal, is I should have used limit notation, right? It's an improper integral after all. So the limit as a goes to infinity from 1 to a of 1 over x dx. And now that's going to equal to the limit as a goes to infinity of ln of the absolute value of x from 1 to a. And now when you evaluate that a in there, we're going to get the limit as a goes to infinity. A lot of work to be shown on this test for sure, but it's just an integral. ln of a minus ln of 1. Now from here, the ln of infinity is going to infinity, right? That's what's going on in my head. This is going to 0. That goes to infinity. therefore, since the integral diverges, the series diverges. So I'll say, therefore, the integral from 1 to infinity of 1 over x dx diverges, and so does the series. And I guess it'll be very formal, from n equals 1 to infinity of 1 over n. Now, again, what we stated here is that we're positive, continuous, and decreasing. That was big. That allowed us to use the integral test. Then we took the integral from the exact same index to the exact same infinity. We found that this thing diverged, the integral did, and therefore the series did. So, tried and true method. We stated the conditions, a lot of conditions here. We stated the name of the test, and we stated the conclusion. All right, let's do another one here. So this one, again, for both of these down the road, we're not going to be using the integral test. There's other tests that come from the integral test that makes it easier, but let's rock this one. Let's expand it out. I plug in 0, I get 0, plus, and now the next one that I'm going to get on this is going to be, well, 1. So it's going to be 1 over 1 cubed plus 1 is 1/2, plus 2. 2 squared is 4. All over 8 plus 1 is 9, so it's 4 9ths, plus 3. 3 squared is 9. All over 27 plus 1 is 28, and so on and so forth. So that's going to keep on going until we get to the nth term, n squared over n cubed plus 1, and so on and so forth after that. Point being is, we've got continuous, positive, and decreasing over the interval. So I'm going to, again, start out with a very formal definition. Since n squared over n cubed plus 1 is, and I am going to abbreviate here, continuous, positive, and decreasing, the integral test, I'll say the int test, will be used. Change up the wording a little bit. All right. So again, those are part of my conditions I have to state. Now I'm going to actually take the integral from that same bound, 0 to infinity. And this thing is continuous from 0 on to infinity. We'll take of x squared over x cubed plus 1, the exact same function that this is, dx. And now we're going to do some integration, but of course we need our limit. The limit as a goes to infinity, because it's an improper integral, from 0 to a. And at this point, you are fully invested in just integrating. Right? You are not worried about anything else other than finding out whether this integral converges or diverges. Now, I'm going to do a little bit of integration magic here and skip a couple of steps because you've seen these kinds of integrals many times. If you need help with the u substitution, go back to chapter 4. If you need help with the improper integrals, go back to chapter 8. It's all there. So this is going to be equal to the limit as a goes to infinity. I just didn't want to overwhelm you with lots of extra stuff that you've already learned. So limit as a goes to infinity of, the integral of this is going to be the ln again, of x cubed plus 1, and that's going to be divided by 3. So you're going to have a 1/3 there, because when you take the derivative of this, you'll get 1 over all of that times 3x squared. So that'll cancel out there. And that's evaluated from 0 to a. Well, that ends up being equal to the limit as a goes to infinity, and maybe beyond, maybe, of 1/3 ln of infinity cubed, essentially. So that's going to end up being, we'll just plug in the a cubed plus 1. And then when you plug in 0 into this, 0 cubed plus 1 is 1. ln of 1 is 0. So I'm going to put minus 0 here. And so then we end up with the limit being plugged in with infinity, and you get 1/3 ln essentially of infinity. Infinity cubed is infinity plus 1, still infinity. And so that equals to infinity. So all I'm going to say is, therefore, the integral from 0 to infinity of, let's see, x squared over x cubed plus 1 dx diverges. And so does, we'll get that there, and so does our original series, n equals 0 to infinity of n squared over n cubed plus 1. That's it. Again, conditions, the limit itself as whatever goes to infinity of that improper integral. Find that improper integral. Since it diverged, so does the original series. Now, what about one that converges? Let's take a look at one of those. So this guy right here, you look at that and you might be like, oh, do we really have to use the integral test here? Well, let's see if it fits the bill. So if I plug in 1, I get 3 over 1 squared and 1 is 2. Then I'll plug in 2. I'll get 3 over 2 squared and 1 is 5. Plus 3 over 3 squared and 1 is 10. Plus 3 over, and I think we get the picture. We're going to be going up by, let's see, well, 7 this time. 4 squared and 1 is 17, and so on and so forth until we get to our nth term. So expanding it out, expansion is your friend. Remember that. And it keeps on going on and on and on. Now, do the terms decrease? They do. Are they all positive? They are. Are we continuous? From n equals 1 on, we are. So I would say since, and again, I'm showing you the most formal way of doing things so that you get full credit on the BC exam or on any college professor or teacher's exams. Since 3 over n squared plus 1 is continuous, positive, and decreasing, we will use the integral test. We will use the integral test. The int test. Again, I'm abbreviating greatly here. Don't do that on a test. All right, now, from here, we're going to take our integral from 1 to infinity. It's a matching integral. So 1 to infinity of 3 over, we'll do x squared plus 1 dx. That's going to be equal to, now here, again, we still need our limit because it's an improper integral. A goes to infinity from 1 to a, or 1 to a. We've got 3 over x squared plus 1. Now, if you don't remember this one, this is the definition of arctangent. And if you don't remember it, go back to the end of chapter 5. It's all up in there. There's a little bit of that in chapter 8 too. So I'm going to assume that you know that because it's been taught before, but if you don't, go back to the end of chapter 5 there for inverse trig derivatives and integrals. Don't know why I did a funky accent there, but there you have it. So this is the limit as a goes to infinity of the antiderivative of that is 3 times the arctan of, and it's just going to be x. It's the perfect arctan definition, and that's evaluated from 1 to a. And that's going to be equal to the limit as a goes to infinity of, and that's going to be 3 arctan, and now we're just going to plug in our values of a minus 3 arctan of 1. All right, not so bad. So let's check out what all of this ends up equaling out to. What's 3 arctan of infinity? Because essentially that's what's happening here, right? You're plugging in infinity, so 3 arctan of infinity. And this one's a little bit tough to figure out. If you take a look at your unit circle here, you're basically saying, when is the tangent of some angle equal to infinity? From negative pi over 2 to pi over 2, because that's what tangent is restricted on. And tangent actually approaches infinity, its vertical asymptote here at pi over 2. That's because the tangent of pi over 2 gives you that cosine of pi over 2 in the denominator, which is 0, making this function rocket up to infinity. So this is actually equal to, believe it or not, we're going to get 3 times arctan of infinity, as I said, pi over 2. That's minus 3 arctan of 1. Well, what's arctan of 1? That's saying the tangent of what value, of what angle equals to 1? Well, that's when our angle is perfectly symmetric with respect to x and y values. That'd be a pi over 4. So that's 3 times pi over 4. And when we simplify all this down, you get 3 pi over 2 minus 3 pi over 4. That ends up actually ending up being 3 pi over 4, because this is 6 pi over 4 minus 3 pi over 4. That is your value. Now, that is not the sum of the series. I need to be very clear. Just because we got out this value doesn't mean that's what this series adds to. So all I'm going to state is, therefore, the integral from 1 to infinity of 3 over x squared plus 1 dx converges, and so does the series. And so does n equals 1 to infinity of 3 over n squared plus 1. So again, very, very important, and maybe I'll put this here in the notes as well, just as we round out. If that converges, then that converges. A little note, this here does not necessarily, in most cases, equal out to your sum from n equals 0 to infinity. It merely states that since the integral converged, the series does. We don't necessarily converge to what the integral converges to. I want to be very clear. All right, I'm going to leave it at that. You rocked it. Heck, heck, we did it together, but you rocked it. I know you got this. I'll see you in the next video where we go over the why behind why the integral test works. Peace.